Hello everyone, welcome to yet another series of video on tensor. This would be the last episode of the tensor that we are continuing as we went through the finding of the basis vectors. Let me just quickly show you the topic. So in this particular video we would be finally concluding what we have learned in the first two episodes, and we will be also looking at how we can relate the topics which we learned earlier along with the Kronecker delta. Well, here you see these are the topics that we are covering. So initially what we did is that we covered the first part, it is finding values in a stress tensor. This is already being done. Basis of vectors, we have already done what are the bases of vectors and through which we can find out the basic essence of vector, that the vector remains invariant but the components of the vector changes. Change of basis of vectors we have already seen. Forward and backward transformations, we have just covered the forward transformation, and here we will cover now the backward transformation and the Kronecker delta part. Just to remind you with another important part, that tensors have components that change in a special predictable way and under the change of coordinates. This is yet another important part, so I am showing it again to you. Tensors have components that change in special predictable way under the change of coordinates. So this is quite important. Just to remind you on a quick note, this should also be taken into account, that forward transformation takes us from the old basis to new basis, and backward transformation takes us from the new basis to old basis. So forward transformation, which we have done, as we have taken old basis to new basis, now we will be doing with the backward transformation, that is from the new basis to old basis, and then we will relate to each other. So just to give you a quick update, or I would just a quick review on what we have done previously in the earlier lesson, this one, right? So we have taken the forward transformation from these from the old basis to the new basis. So we are finding out the new basis based on the old basis. So this is the forward transformation. We have drawn the matrix, and this is how we sum up the entire forward transformation, keeping in the scripts in mind. FGI, J varies from 1 to n. Now what we will do is that we will take into account the backward transformation. So more or less it would be the same thing, so nothing would change, only that we would be finding out the backward transformation. That means on the left hand side we will write the this on the left hand side we were writing the old basis based on which we will be finding out the new basis. So let us do the this part on the paper. So now what we are doing is the backward problem. So I will just write it down for you. This would be the backward problem. Backward transformation. So I just put it as backward transformation. Right, so currently we would be doing the backward transformation. So what is the backward transformation that we have, which we have noted earlier, is that we will just take E1, and from there we would be finding backwards. So we will put it as B as for backward. So the first matrix would be 1 1. I need to change the color of the pen constantly, so I will put it as E1 tilde, right, followed by B21. So we will add up this plus B21, right, then E2 tilde, E2 bar tilde, right, then we will further take E2, right, E2 would be equal to B11, then it will come to B12, then we will take the E1 tilde, right, plus B21 will change to B22, right, so we are deriving this B22, and this would be E2 tilde, right, E1, yeah, E2 tilde, right, and this would be going on. So we can write the backward transformation matrix as B equals to, I'll just put it across, it would be B11, here it would be B12, this would be B21, this would be B22, right. So now what we do in the same way that we did, we are now doing for n dimensions. So I will just put it as for n dimensions. So for n dimensions, what we can write E1 would be equal to B11, then E1 tilde plus B21 E2 tilde plus this would continue dot up to Bn1 En tilde. Similarly, we will draw the E2 part up to n. So E2 would be equal to B21 1 2. I'm so sorry, 1 1, then changing to 1 2 E1 tilde plus B22, then E2 tilde plus dot it would go to Bn2 and En tilde. This would be tilde, right? And then we will do it therefore for En. So let us do it for En. So for En it would be equal to B1n, right, E1 tilde plus B2n and E2 tilde plus dot and it would be continuing till Bnn En tilde, right? So this is a generalization form. So it started with 1 1, then 1 2, and then 1 nn. So we can put it again in a piece of a matrix. So let us write it for this time. So it would be B11 B21 dot it would take up to Bn1, right, this part. Then it would be B12 B22 dot up to Bn2, right? Then we have got here B1n, then B2n dot up to Bnn. So we can put this as a part of the matrix, right? So again, let us generalize it in a general form. So what we are going to do is that we are going to be very careful about the subscripts and the indices. So I can write EI, right, which would be equal to a summation of j equals to 1 to n, because it will be I and j, row and column. It would be bji, right, and then we will have ej tilde, right? So this actually sums up the entire method of writing in this big way. We can summarize it in this way: ei, j wants to n, bji, and equals to ij. If you see the previous one, what we have done is this one: ei tilde equals to j, fji equals to ej, which is, we put an arrow over that, and it's the same. So you see, if I put this side by side, what you can see, this one, this is the red one, so we have found it from the forward transformation, so from here to here, and in the backward we have found this part remains here, and this is the backward transformation, so it summarizes the entire part. So we can also sum up from here that to sum up, the bji tells how much of ej ends up in ei. So bji tells how much of ej, this one, yeah, how much of this one will end up in ei, right? So that is how. So can we sum it up in a brief equation? So let us write it in this way. So to sum it up, what we can write over here is that, yeah, so we can write ej, okay, ej, because we are trying to find out the ej part. Ej tilde, okay, equals to sigma of k equals to 1 to n f of kj ek, right? That is how we sum it up. And the second part would be ei equals to sigma of j equals to 1 to n b, this would be ji, right, of ej tilde, right? So this sum it up both the two equations in a nice fashion. So we don't have to write it in a very big way, so we can just sum it up. Now what we need to do is that can we prove that ej, this part, and ei are inverse to each other? See, you need to understand the basic essence of providing these two matrices is that if we can prove that these are inverses of each other, then in a mathematical way we can find out the transformation part very easily. We can find out the transformation part easily. So now we will just quickly look into how we can prove that these two are inverses. Now in order to prove the inverses, I will just summarize this entire part. I need to write it once more, right? So let me write it for you. So here what will happen is that we will write ej tilde would be equals to, I'm just sum it up once more so that it lies right in front of your eyes. It would be sigma, okay, of k equals to 1, the upper limit would be n because we are making it for n dimensions. It would be fkj and ek, right, this one. And then we have another where we need to write ei equals to sigma of j equals to 1 to n, and it would be subscript would be bji, right, of ej tilde. So the red one and the blue one and the red one and the black one will remind you that what is the vectors, that is the first one and the right one. So you see here what we have done in the previous one. I would like to show you. This is the one. So we got ej fkj going up to ek and the bji to ej tilde. So we are just finding it. We are writing it one more time, right? Now you see that, so starting with the backward transformation, we'll start with the backward transformation. So I will write here starting with b, that is a backward transformation. What I can write is that for the backward transformation, the equation would be ei, right, equals to sigma j equals to 1 to n, right, b ji and ej tilde, right? But just note one thing, that this ej arrow tilde is this one. So what we can do over here is that from here I can just substitute the value of ej over here. I can just substitute this value over here. So what will come, I need to arrange these summations. So I can write ei equals to sigma, okay, sigma j, because here we are doing the summation, bji, right, and within bracket I write sigma k, right, fkj ek, right, put the braces over here, and then further we can write ei, right, equals to sigma of k, and then I put a bracket, I put sigma, it would be j, right, bji fkj, and this would be outside, so it would be ek, right? So what we are doing is that we are building up old basis vectors using E1 and using a summation, say this one to this one. So we are building up old basis vectors E1 using summation of old basis vectors. That means, say for example, let me use a different color, you will understand. That means what we are trying to do over here, just pay attention. So you will see from E1 we are going to something like E1, right? And then from E2 we are building up E2, right? So we don't want any extra dimensions or plus or something over there, right? And in this way what we will do is that we will make up something like En going up to En, right? This is basically what we are trying to do. So we are building up old basis vectors E1 using a summation of old basis vectors. So now I will put a different color and we will write it something like this. So using a little bit of summation, I'm not going over to describe this sigma part, otherwise it will take a long time. So you can do your own calculations to see whether I have done right or wrong. So I can write EI equals to sigma of k, right? Sigma of k, then let me put another bracket and I will put sigma j, right, bji, okay, f of kj, and then I put a bracket ek, right? So now you see that what we are trying to do is that we are trying to get 0 and 1. So what we can do, so this middle part is what we are worried about, this part. So this would be 1, okay, when I equals to k, right? And this would be 0 when I is not equals to k. I is not equal to k. So this would be something we are doing. So we can write that. So we can write b, right, ji, okay, fkj, right, equals to what? Like it would be equal to, say for example, if I equals to k, right? If I equals to k, then it would be 1, right? And if I is not equal to k, then 0, right? So this is something which we are trying to prove. This is something which we are trying to get over. So b of ji fkj, this middle part, we are trying to make it 1 or 0, so that when I equals to k and I is not equal to k. Now if you see that this phenomena of I and k has become so common that we have put up a common term. So I'll just show you how does it happen. So let us see, I'm not going to derive that part, but I will just going to show you. Let me use the color blue so that you can understand this is something different. So you see here, so let me write, so if I equals to rho, okay, I equals to rho and k equals to column. So if I equals to rho and k equals to column, when I put 1, right, when I'm putting 1, then I equals to k. I equals to k, that means rho equal to the column. Rho becomes equal to the column if I put I equals to k. So what we essentially get over here, okay, we get something like this, 1 0 0, then we get 0 1 0, and we get 0 0 1. So diagonally see we are getting 1, which proves that it is a unit matrix, and this is something that we call as Kronecker delta, Kronecker. It is called a Kronecker delta, and it is given by this kind of a sign. right? It is given this kind of a sign. So again, let us put it how it will look. And when I equals to row and k equals to column, how it will look like? It will look like something like this. So we put Kronecker 1 1, Kronecker 1 2, Kronecker 1 3, then Kronecker 2 1, Kronecker 2 2, Kronecker 2 3, then we put Kronecker 3 1, Kronecker 3 2, Kronecker 3 3, right? This becomes a matrix, and it would be looking something exactly like this. So it will have 1 0 0 0 1 0 and 0 0 1, and this is wall 1. That means it is a unique matrix. So we can call this as unit matrix, right? And as you see, this part will become true given the conditions that Kronecker ik equals to, within braces, 0 if I equals to k, 1 if I is not equal to k. This is quite a simple matrix manipulation. If I equals to k, then it will become what? 1, then again 0, again 0. In this way we get it. So this one is a unit matrix. The unit matrix, what does it prove? What does it prove? It proves that the forward and the backward transformations are inverses to each other, right? So I can always take a final conclusion over here that the forward given by f, right, I will just put it like this, and backward transformations b are inverses to each other, are inverses. Because see, what we have done from here is that with the backward transformation calculation, if you see, what we have done is that we have got this and this, right? And then we have substituted the values of this. If I may show you this one, right? So from E1, E1, E2, E2 and so on, we are going over here, and we are trying to make the middle part 1 and 0. And that is why it becomes so common that it is used in Einstein's general theory of relativity. We will see when we come to the Einstein field equation, this Kronecker-delta. So Kronecker-delta gives us a unit matrix, which means that the forward and backward transformation are inverses, and inverse means that if f is something, b is exactly the opposite. So now we will write the final equation. So we can write now, so let me put it in the final. So we write sigma of j, right, f of f subscript kj, okay, then we have got the backward bji equals to Kronecker ik, this is the row and the column, and this would be equal to, given a condition, if I equals to k, then 1, if I is not equal to k, then 0. So this is the final, what we sum up, that is the forward and the backward transformations equals to the Kronecker of ik. And in this way, if I take f and b as forward, therefore I can write f multiplied by b inverse is, these are inverse, f and b are inverses. So that brings us to the end of the video, but finally we would just like to quickly take a note on the indices part, because it has been a little bit confusing between j and k and I and j. So what I would like to show you is that how the indices are related to each other and what index tells what. So for that I need to write down the indices once more for you. So we start with ej tilde. So you let me write it for you, ej tilde. Okay, let me use the blue color. Okay, no, fine, we will use the black one, because otherwise we will lose the convention. This would be equal to sigma of k equals to 1 to n, right? These are the two most important parts that we have got. Then we have got forward kj, fkj, ek, right? And then we can write the next one, EI would be equal to sigma this time it would be j equals to 1 to n, j equals to 1 to n. Then we got the backward b, right? bji, and then we have used the red one, ej tilde, right? So now you see the index that we do the summation with the first letter tells us this part. I will just write it once more for you. So see, okay, let us start with this one, fkj, right? The first index, this one, fk, will be equal to k equals to 1, this one. So I can just, I'm using this as a code, it implies, okay, don't take it as some kind of a mathematical symbol. So if we are just writing, say for example, fkj, this is correspond to k. First index goes to the first index, this one goes to this one. Similarly for bji, you will see bji, it also corresponds to the first letter j, and this is corresponding to j, right? So this is the first one, this is the first pair of indices, right? Also the basis vectors, that is bji, okay, let me find out fkj, yeah, j equals to 1, this j equals to 1, okay. Then we will see that fkj, okay, this k is also, this one fkj, this k is also equal to the basis vector. These are basis vectors, right? This also corresponds to ek, right? This corresponds to ek, this k and this k, right? And similarly bji will correspond to ej, right? So this j and this j. So this is one part. So index, the first index that use the summation, that is for fkj, it will correspond to the values of the summation of k. For bji, j, and this one, this k and the basis vector k, bj will be equal to bj. I will use a different color for the second letter part. So for the second letter, let me use the red one. Yeah, so not the red one, I would like to use the blue one, okay, or the green one. Yeah, so for the second letter, so we have got fkj, okay, second letter j, this one, right? This will correspond to ej, right, which is the output vector. So remember, I will just put an arrow and write it over here. This is the output vector. This is the output vector. So fkj, this j will be related, will be corresponding to this j, and so this one, fkj, this one will be relating to this one, and bji, see this one would be corresponding to this one. This is I, okay, there's a dot in it, right? So bji will be corresponding to ei, right? This one, ei. So this one is ej, but I have to put a, anyway, I am not putting the tilde part. So this is again the output vector. This is important because without this you will get confused with the indices part. So indices is again very important. So fkj, it will equal to ej tilde. Let me see if I have missed it. bji equal to ej. This would be again a tilde. This is fine. ek has got no tilde. Yeah, this is fine. So this is important. Just a quick note that the review, while you're doing the index, you need to note the summation index. This k and this k would be equal. J will be equal to j. The second letter j, the second letter of j, yeah, this one would be equal to this one, and this one will be equal to this one, right? So the output, this one, yeah. So fkj equals to j, and fk, yeah, this one, this k is equals to this k, and this one, bji will be equal to this one. Okay, what else? Let me see. Yeah, so yeah, so fkj equals to 1, this di, and Okay, yeah, this part will be also, this one is the first index for the summation, this j and this j. This one is for the output vector, mind it. This one is the summation, same first index goes for output. So the first would be the k, that is, this is for the summation. Let me write it for you. This is the summation part. This is the second letter which will be go for the other part. In the same way we have seen that fkj is second, this is the first letter part. This is entirely the first letter, first index you can call it, right? This is the second index. This part is the second index, right? This is second index. So first index we see the summation, this and this corresponds to this corresponds to this. Second index what we see is the output vector. So this part will be equal to the this part ej with a tilde, and this part will be equal to this part bji, this one. So this is the output vector of the forward transformation, this is the output vector of the backward transformation. So this has finally got us our end to the video. It has been 3 topics that we almost covered. So I will just like to quickly tell you what are the, have we covered the topics. So this is the tensor part. So you see here we have covered finding the values in a stress tensor. We have already done this. Basis of vectors, we have done this. Change of basis of vectors, we have shown this. Forward and backward transformation has been covered in 2 videos, and we have finally covered also the Kronecker delta part. Just a quick review. Remember that tensor has components that change in a special predictable way. We have seen that under the change of coordinates. Forward and backward transformation. Forward transformation takes us from the old basis vector to the new basis vector, and backward transformation from the new basis vector to the old basis vectors. So this has been quite a long one. I hope you liked it because we have covered almost everything in the part, the forward, the backward and everything. We have also covered how change of coordinates actually looks into the change of vectors. The change in vectors, like I mean to say, for example, we have changed the vector v, and we have seen that vector v actually doesn't change, but the components change. So that is what is called the change in basis of vectors. And then we have finally shown that how it is related to Kronecker delta, and most importantly that the Kronecker delta and f and b are inverses. So this gives us a kind of a mathematical tool in which we can find out further as we look into Einstein's field equation, covariant, contravariant vectors, and most importantly the metric tensor part. We will be coming to those topics one by one. So this is how it concludes the video. I think you have liked it. If you have any comments, please put it up, and you can go forward watching my next videos, which would be continuing with the series in tensor. Thank you very much. Have a nice day and stay well. Bye.